What's up everybody, Adel here. Today's video is a collection of course videos covering all things you need to know about NLP and Python. In this part 1 of this crash course, we're going to cover all you need to know about tokenization using tools like spaCy and NLTK, using regular expressions to manipulate text data, preprocessing text data for tasks like machine learning or sentiment analysis, and a lot more. If you enjoy these videos, make sure to let us know in the comments, subscribe to the channel, and if you want to learn interactively and actually apply what you learned today, make sure to check out the courses linked in the description below. And with that, happy learning.
Welcome to the course. In this video, you'll be learning about regular expressions. Natural language processing is a massive field of study and actively used practice, which aims to make sense of language using statistics and computers. In this course, you will learn some of the basics of NLP, which will help you move from simple to more difficult and advanced topics. Even though this is the first course, you will still get some exposure to the challenges of the field, such as topic identification and text classification. Some interesting NLP areas you might have heard about are topic identification, chatbox, text classification, translation, and sentiment analysis. There are also many more. You will learn the fundamentals of some of these topics as we move through the course. Regular expressions are strings that you can use that have a special syntax, which allows you to match patterns and find other strings. A pattern is a series of letters or symbols, which can map to an actual text or words or punctuation. You can use regular expressions to do things like find links in a web page, parse email addresses, and remove unwanted strings or characters. Regular expressions are often referred to as regex and can be used easily with Python via the RE library. Here we have a simple import of the library. We can match a substring by using the RE_match method, which matches a pattern with a string. It takes the pattern as the first argument, the string as the second argument, and returns a match object. Here we see it match exactly what we expected, A, B, C. We can also use special patterns that regex understands, like the \W+, which will match a word. We can see here, via the match object representation, that it has matched the first word it found, hi. There are hundreds of characters and patterns you can learn and memorize with regular expressions, but to get started, I just wanted to share a few common patterns. The first pattern, \W, we already saw. It's used to match words. The \D pattern allows us to match digits, which can be useful if you need to find them and separate them in a string. The \S pattern matches spaces. The period is a wildcard character. The wildcard will match any letter or symbol. The plus and asterisk characters allow things to become greedy, grabbing repeats of single letters or whole patterns. For example, to match a full word rather than just one character, we need to add the plus symbol after the \W. Using these character classes as capital letters negates them, so \S matches anything that is not a space. You can also create a group of characters you want by putting them inside square brackets, like our lowercase group. In the following exercises, you'll use the RE module to perform some simple activities, like splitting on a pattern or finding all patterns in a string. In addition to split and find all, search and match are also quite popular. You saw a simple match at the beginning of this video, and search is similar, but it doesn't require you to match the pattern from the beginning of the string. The syntax for the regex library is always to pass the pattern first and the string second. Depending on the method, it may return an iterator, a new string, or a match object. Here, we see the RE_split method will take a pattern for spaces and a string with some spaces and return a list object with the results of splitting on spaces. This can be used for tokenization, so you can pre-process text using regex while doing natural language processing. In this video, we'll learn more about string tokenization. Tokenization is the process of transforming a string or document into smaller chunks, which we call tokens. This is usually one step in the process of preparing a text for natural language processing. There are many different theories and rules regarding tokenization, and you can create your own tokenization rules using regular expressions. But normally tokenization will do things like break out words or sentences, often separate punctuation, or you can even just tokenize parts of a string, like separating all hashtags in a tweet. One library that's commonly used for simple tokenization is NLTK, the Natural Language Toolkit library. Here is a short example of using the word tokenize method to break down a string into tokens. We can see from the result that words are separated and punctuation are individual tokens as well. So why bother with tokenization? Because it can help us with some simple text processing tasks, like mapping parts of speech, matching common words, and perhaps removing unwanted tokens like common words or repeated words. Here we have a good example. The sentence is, "I don't like Sam's shoes." When we tokenize it, we can clearly see the negation in the not, and we can see possession with the apostrophe S. These indicators can help us determine meaning from simple text. Beyond just tokenizing words, NLTK has plenty of other tokenizers you can use, including these ones that you'll be working with in this chapter. The sent_tokenize function will split a document into individual sentences. The Regex tokenize uses regular expressions to tokenize the string, giving you more granular control over the process. And the tweet tokenizer does neat things like recognize hashtags, mentions, and when you have too many punctuation symbols following a sentence. How convenient. You'll be using more regex in this section as well, not only when you're tokenizing, but also figuring out how to parse tokens in text. Using the regex modules rematch and research are pretty essential for Python string processing. Learning when to use search versus match can be challenging, so let's take a look at how they're different. When we use search and match with the same pattern and string when the pattern is at the beginning of the string, we can see we find identical matches. This is the case with matching and searching ABCDE with the pattern ABC. When we use search for a pattern that appears later in the string, we get a result, but we don't get the same result using match. This is because match will try and match a string from the beginning until it cannot match any longer. Search will go through the entire string to look for match options. If you need to find a pattern that might not be at the beginning of the string, you should use search. If you want to be specific about the composition of the entire string, or at least the initial pattern, then you should use match. In this video, we'll take a look at doing more advanced tokenization with regex. One new regex pattern that you'll find useful for advanced tokenization is the ability to use the OR method. In regex, OR is represented by the pipe character. To use the OR, you can define a group using parentheses. Groups can be either a pattern or a set of characters that you want to match. You can also define explicit character ranges using square brackets. We'll go into a bit more depth on groups and ranges soon. Let's take an example that we want to tokenize using regular expressions, and we want to find all digits and words. We define our pattern using a group with the OR symbol, and we make them greedy so they catch the full word or digits. Then we can call findAll using Python's RE library and return our tokens. Notice that our pattern does not match punctuation, but properly matches the words and digits. Let's take a look at another more advanced topic, defining groups and character ranges. Here we have another chart of patterns, and this time we're using the ranges or character classes marked by the square brackets and groups marked by the parentheses. We can see in this chart that we can use square brackets to define a new character class. For example, we can match all upper and lowercase English letters using uppercase A hyphen uppercase Z, which will match all uppercase letters, and then lowercase a hyphen lowercase z, which will match all lowercase letters. We can also make ranges to match all digits, 0-9, or perhaps a more complex range like uppercase and lowercase English with the hyphen n period. Because the hyphen and period are special characters in regex, we must tell regex that we mean an actual period or hyphen. To do so, we use what is called an escape character. In regex, that means to place a backward slash in front of our character so it knows then to look for a hyphen or a period. On the other hand, with groups which are designated by the parentheses, we can only match what we explicitly define in the group. So A hyphen Z match only A a hyphen, and Z. Groups are useful when you want to find an explicit set of characters, such as the final example, where we're taking spaces or commas. In this code example, we use match with a character range to match all lowercase ASCII, any digits, and spaces. It is greedy, marked by the plus after the range definition, but once it hits the comma, it can't match anymore. This short example demonstrates that thinking about what regex method you use, such as search versus match, and whether you define a group or a range can have a large impact on the usefulness and readability of your patterns. Hi everyone! In this video, we're going to learn about using charts with our NLP tools. Matplotlib is a library used by many different open source Python projects to create data visualizations, charts, and graphs. It has fairly straightforward functionality, with lots of options for graphs like histograms, bar charts, line charts, and scatter plots. It even has advanced functionality, like generating 3D graphs and animations. Matplotlib is usually imported by simply aliasing the pyplot module as plt. If we want to plot a basic histogram, which is a type of plot used to show distribution of data, we can pass in a small array to the hist function. The array has 5 appearing twice, and 7 appearing 3 times, so it's a good candidate to show distribution. Finally, we call the plot.show function, and Matplotlib will show us the generated chart in our system standard graphics viewing tool. This is the chart that we generated using the previous code. We notice that indeed it has determined proper bins for each entry, and we can see that the 7 and 5 bins reflect the distribution we expected to see. It's not the prettiest chart by default, but making it look nicer is fairly easy with more arguments and several available helper libraries. We can then use skills we've learned throughout this first chapter to tokenize text and chart word length for a simple sentence. First, we perform the necessary imports to use NLTK for word tokenization and Matplotlib charting. Then, we tokenize the words and punctuation in a short sentence. Finally, we can use Python list comprehension with our tokenized words array to transform it to a list of lengths. As a brief refresher on list comprehensions, it is a succinct way to write a for loop. If we look at the syntax, we have opening and closing square brackets. Then we can iterate over any list and make it a new list using this simple syntax. Here we create a list that holds the lengths of each word in the words array simply by saying len w for w in words. This will iterate over each word, calculate the length, and return it as a new list. We then pass this array of token lengths to the hist function and generate our chart using the plot.show function. Here is the generated histogram from our previous code. We can see from the chart that we have a majority of 4-letter words in our example sentence. Of course, with a simple sentence, that's easy enough to simply count by hand. But for an entire play or book, this would be tedious and prone to error, so writing it in code makes it a lot easier. Welcome to Chapter 2. We'll begin with using word counts with a bag of words approach. Bag of words is a very simple and basic method for finding topics in a text. For bag of words, you'll need to first create tokens using tokenization, and then count up all the tokens that you have. The theory is that the more frequent a word or token is, the more central or important it might be to the text. Bag of words can be a great way to determine the significant words in a text based on the number of times that they are used. Here we see an example series of sentences, mainly about a cat and a box. If we just use a simple bag of words model with tokenization like we learned in Chapter 1 to remove the punctuation, we can see the example result. Box, cat, uppercase T, the, and lowercase t, the, are some of the most important words because they are the most frequent. Notice the word the appears twice in the bag of words, once with uppercase and once lowercase. If we added a pre-processing step to handle this issue, we would lowercase all of the words in the text, so each word is counted only once. We can use the NLP fundamentals we already know, such as tokenization with NLTK, to create a list of tokens. We will use a new class called counter, which we import from the standard library module collections. The list of tokens generated using word tokenize can be passed as the initialization argument for the counter class. The result is a counter object, which has a similar structure to a dictionary and allows us to see each token and the frequency of the token. Counter objects also have a method called most common, which takes an integer argument, such as 2, and returns the top 2 tokens in terms of frequency. The return object is a series of tuples inside a list. For each tuple, the first element holds the token, and the second element represents the frequency. Note, other than ordering by token frequency, the most common method does not sort the tokens it returns or tell us that there are more tokens with the same frequency. In this video, we will cover some simple text preprocessing. Text preprocessing helps make for better input data when performing machine learning or other statistical methods. For example, in the last few exercises, you have applied small bits of preprocessing, like tokenization, to create a bag of words. You also notice that applying simple techniques like lowercasing all the tokens can lead to slightly better results for a bag of words model. Preprocessing steps like tokenization or lowercasing words are commonly used in NLP. Other common techniques are things like lemmatization or stemming, where you shorten the words to their root stems, or techniques like removing stopwords, which are common words in a language that don't carry a lot of meaning, such as and the, or removing punctuation or other unwanted tokens. Of course, each model and process will have different results, so it's good to try a few different approaches to preprocessing and see which works best for your task and goal. We have here some example input and output text that we might expect from preprocessing. First, we have a simple 2-sentence string about pets. Then we have some example output tokens we want. You can see that the text has been tokenized and that everything is lowercase. We also notice that stopwords have been removed and the plural nouns have been made singular. We can perform text preprocessing using many of the tools we already know and have learned. In this code, we are using the same text as from our previous video, a few sentences about a cat with a box. We can use list comprehensions to tokenize the sentences, which we first make lowercase using the string lower method. The string isAlpha method will return true if the string only has alphabetical characters. We can use the isAlpha method along with an if statement iterating over our tokenized result to only return alphabetic strings. This will effectively strip tokens with our numbers or punctuation. To read out the process in both code and English, we say that we take each token from the word tokenize output of the lowercase text if it contains only alphabetical characters. In the next line, we use another list comprehension to remove words that are in the stopwords list. This stopwords list for English comes built in with the NLTK library. Finally, we can create a counter and check the 2 most common words, which are now cat and box, unlike the and box, which were the 2 tokens returned from our first result. Preprocessing has already improved our bag of words and made it more useful by removing the stopwords and non-alphabetic words. In this video, we will get started using a new tool called Gensim. Gensim is a popular open-source natural language processing library. It uses top academic models to perform complex tasks like building document or word vectors, corpora, and performing topic identification and document comparisons. You might be wondering what a word or document vector is. Here are some examples in visual form. A word embedding or vector is trained from a larger corpus and is a multidimensional representation of a word. You can think of it as a multidimensional array, normally with sparse features, which means lots of zeros and some ones. With these vectors, we can then see relationships among the words or documents based on how near or far they are, and also what similar comparisons we find. For example, in this graphic, we can see that the vector operation king minus queen is approximately equal to man minus woman, or that Spain is to Madrid as Italy is to Rome. The deep learning algorithm used to create word vectors has been able to distill this meaning based on how those words are used throughout the text. The graphic we have here is an example of LDA visualization. LDA stands for Latent Dirichlet Allocation and is a statistical model that we can apply to text using Gensim for topic analysis and modeling. This graph is just a portion of a blog post written in 2015 using Gensim to analyze US presidential addresses. The article is really neat, and you can find the link here. Gensim allows you to build corpora and dictionaries using simple classes and functions. A corpus, or if plural, corpora, is a set of texts used to help perform natural language processing tasks. Here, our documents are a list of strings that look like movie reviews about space or sci-fi films. First, we need to do some basic preprocessing. For brevity, we will only tokenize in lowercase. For better results, we would want to apply more of the preprocessing we've learned in this chapter, such as removing punctuation and stopwords. Then we can pass the tokenized documents to the Gensim dictionary class. This will create a mapping with an ID for each token. This is the beginning of our corpus. We can now represent whole documents using just a list of their token IDs and how often those tokens appear in each document. We can take a look at the tokens and their IDs by looking at the token2ID attribute, which is a dictionary of all our tokens and their respective IDs. Using the dictionary we built in the last slide, we can then create a Gensim corpus. This is a bit different than a normal corpus, which is usually just a collection of documents. Gensim uses a simple bag of words model, which transforms each document into a bag of words using the token IDs and the frequency of each token in the document. Here we can see that the Gensim corpus is a list of lists, each list item representing one document. Each document is now a series of tuples, the first item representing the token ID from the dictionary, and the second item representing the token frequency in the document. In only a few lines, we have a new bag of words model and corpus thanks to Gensim. And unlike our previous counter-based bag of words, this Gensim model can be easily saved, updated, and reused thanks to the extra tools we have available in Gensim. Our dictionary can also be updated with new texts and extract only words that meet particular thresholds. We're building a more advanced and feature-rich bag of words model, which can then be used for future exercises. In this video, we'll learn how to use a Tf-Idf model with Gensim. Tf-Idf stands for Term Frequency Inverse Document Frequency. It is a commonly used natural language processing model that helps you determine the most important words in each document in the corpus. The idea behind Tf-Idf is that each corpus might have more shared words than just stopwords. These common words are like stopwords and should be removed or at least downweighted in importance. For example, if I'm an astronomer, sky might be used often, but it's not important, so I want to downweight that word. Tf-Idf does precisely that. It will take texts that share common language and ensure the most common words across the entire corpus don't show up as keywords. Tf-Idf helps keep the document-specific frequent words weighted high and the common words across the entire corpus weighted low. The equation to calculate the weights can be outlined like so. The weight of token I in document J is calculated by taking the term frequency, or how many times the token appears in the document, multiplied by the log of the total number of documents divided by the number of documents that contain the term. Let's unpack this a bit. First, the weight will be low if the term doesn't appear often in the document because the Tf variable will then be low. However, the weight will also be low if the logarithm is close to 0, meaning the internal equation is low. Here we can see if the total number of documents divided by the number of documents that have the term is close to 1, then our logarithm will be close to 0. So words that occur across many or all documents will have a very low Tf-Idf weight. On the contrary, if the word occurs in only a few documents, that logarithm will return a higher number. You can build a Tf-Idf model using Gensim and the corpus you developed previously. Taking a look at the corpus we used in the last video around movie reviews, we can use the bag of words corpus to translate it into a Tf-Idf model by simply passing it in initialization. We can then reference each document by using it like a dictionary key with our new Tf-Idf model. For the second document in our corpus, we see the token weights along with the token IDs. Notice there are some large differences. Token ID 10 has a weight of 0.77, whereas tokens 0 and 1 have weights below 0.18. These weights can help you determine good topics and keywords for a corpus with shared vocabulary. Welcome to our first video on named entity recognition. Named entity recognition, or NER for short, is a natural language processing task used to identify important named entities in the text, such as people, places, and organizations. They can even be dates, states, works of art, and other categories, depending on the libraries and notation that you use. NER can be used alongside topic identification or on its own to determine important items in the text or answer basic natural language understanding questions such as who, what, when, and where. For example, take this piece of text, which is from the English Wikipedia article on Albert Einstein. The text has been highlighted for different types of named entities found using the Stanford NER library. You can see the dates, locations, people, and organizations found, and extract information from the text based on these named entities. You can use NER to solve problems like fact extraction, as well as which entities are related using computational language models. For example, in this text, we can see that Einstein has something to do with the United States, Adolf Hitler, and Germany. We can also see by token proximity that Bertrand Russell and Einstein created the Russell-Einstein Manifesto, all from simple entity highlighting. NLTK allows you to interact with named entity recognition via its own model, but also the aforementioned Stanford library. The Stanford library integration requires that you perform a few steps before you can use it, including installing the required Java files and setting system environment variables. You can also use the Stanford library on its own without integrating it with NLTK or operate it as an API server. The Stanford Core NLP library has great support for named entity recognition, as well as some related NLP tasks, such as co-reference or linking pronouns and entities together, and dependency trees to help with parsing meaning from relationships amongst words or phrases in a sentence. For our simple use case, we will use the built-in named entity recognition with NLTK. To do so, we take a normal sentence and pre-process it via tokenization. Then we can tag the sentence for parts of speech. This will add tags for proper nouns, pronouns, adjectives, verbs, and other parts of speech that NLTK uses based on an English grammar. When we take a look at the tags, we see that new and York are tagged NNP, which is the part of speech tag for a proper noun, singular. Then we pass this tag sentence into the anyChunk function, or named entity chunk, which will return the sentence as a tree. NLTK's trees might look a bit different than trees you use in other libraries, but they do have leaves and subtrees representing more complex grammar. This tree shows the named entities tagged as their own chunks, such as GPE, or Geopolitical Entity for New York, or MoMA and Metro as organizations. It also identifies Ruth Reichel as a person. It does so without consulting a knowledge base like Wikipedia, but instead uses trained statistical and grammatical parsers. In this video, we'll take a look at spaCy, another great library for natural language processing. spaCy is an NLP library similar to Gensim, but with different implementations, including a particular focus on creating NLP pipelines to generate models and corpora. spaCy is open source and has several extra libraries and tools built by the same team, including DisplayCy, a visualization tool for viewing parse trees, which uses Node.js to create interactive text. For example, if we use the DisplayCy Entity Recognizer Visualizer, which has a live demo online, we can enter the sentence used in the last video. Here, we can see that spaCy has identified 3 named entities and tagged them with the appropriate entity label, such as location or person. spaCy also has tools to build word and document vectors from text. To start using spaCy for named entity recognition, we must first install it and download all the appropriate pre-trained word vectors. You can also train vectors yourself and load them, but the pre-trained ones let us get started immediately. We can load those into an object, NLP, which functions similarly to our Gensim dictionary and corpus. It has several linked objects, including entity, which is an entity recognizer object from the pipeline module. This is what's used to find entities in the text. Then we load a new document by passing a string into the NLP variable. When the document is loaded, the named entities are stored as a document attribute called ents. We see spaCy has properly tagged and identified the 3 main entities in the sentence. We can also investigate the labels for each entity by using indexing to pick out the first entity and the label underscore attribute to see the label for that particular entity. Here we see that the label for Berlin is GPE, or geopolitical entity. spaCy has several other language models available, including advanced German and Chinese implementations. It's a great tool, especially if you want to build your own extraction and natural language processing pipeline quickly and iteratively. So why use spaCy for NER? Outside of being able to integrate with other great spaCy features like easy pipeline creation, it has a different set of entity types and often labels entities differently than NLTK. In addition, spaCy comes with informal language corpora, allowing you to more easily find entities in documents like tweets and chat messages. It's a fast-growing library, so it might even have more supported languages by the time you're watching this video. In this video, we'll review multilingual named entity recognition using a new library, Polyglot. Polyglot is yet another natural language processing library, which uses word vectors to perform simple tasks such as entity recognition. You might be wondering, why do I need to learn another library that uses word vectors? Don't I already have Gensim and spaCy? And you would be correct. The main benefit and difference of using Polyglot, however, is the wide variety of languages it supports. Polyglot has word embeddings for more than 130 languages. For this reason, you can even use it for tasks like transliteration, as shown here, translating some English text into Arabic. Transliteration is the ability to translate text by swapping characters from one language to another. Of course, any user of Google Translate or its competitors has seen issues in translation created by word vectors, but Polyglot is a pretty neat open source tool to have for so many languages. Instead of transliteration, we're going to use Polyglot to perform named entity recognition for some new languages. Similar to spaCy, you need to have the proper vectors downloaded and installed before you begin. Once you do, Polyglot does not need to be told which language you're using. It uses the language detection model to do so when the text object is initialized by passing in the document string. Here is a recent headline from the newspapers in Madrid about the promotion of Madrid by another Spanish politician. If you know Spanish, or even if you don't and you just take a look at the capitalized words, you can see quite a few titles, locations, and people. When we call the entities attribute of the text object, we can see a list of entity chunks Polyglot found while parsing the text. Each chunk has a label, represented by the symbols starting with I, such as IORG, representing an organization, ILOC, representing a location, and IPER, representing a person. You may notice some possible duplication in the first 2 entities found, separating Generalitat de and Catalunya. This makes some sense because the phrase represents both a location, Catalunya, and the organization, the Generalitat. That said, you may need to clean up entities when they don't match your expected labels or have substrings you would rather not track. In this video, we'll be learning about supervised machine learning with NLP. Throughout this chapter, you'll be using these skills and ideas applied to classifying fake news. Supervised learning is a form of machine learning where you're given or create training data. This data has a label or outcome which you want the model or algorithm to learn. One common problem used as a good example of introductory machine learning is the Fisher's iris data. We have a few example rows of it here. The data has several features: sepal length and width, and petal length and width. The label we want to learn and predict is the species. This is a classification problem, so you want to be able to classify or categorize some data based on what you already know or have learned. Our goal is to use the dataset to make intelligent hypotheses about the species based on the geometric features. But instead of using geometric features like the iris dataset, we need to use language. To help create features and train a model, we will use Scikit-Learn, a powerful open source library. One of the ways that you can create supervised learning data from text is by using bag of words models, or Tf-Idf, as features. Let's say I have a dataset full of movie plots and genres from the IMDb database, as shown in this chart. I've separated out the action and sci-fi movies, removing any movies labeled both action and sci-fi. I want to predict whether a movie is action or sci-fi based on the plot summary. The dataset we've extracted has categorical features generated using some preprocessing. We can see the plot summary and the sci-fi and action columns. The sci-fi column is 1 for movies that are sci-fi and 0 for movies that are action. The action column is the inverse of the sci-fi column. In the next video, we'll use Scikit-Learn to predict a movie genre from its plot. But first, let's review the supervised learning process as a whole. To begin, we collect and preprocess our data. Then we determine a label. This is what we want the model to learn. In our case, the genre of the movie. We can split our data into training and testing datasets, keeping them separate so that we can build our model using only the training data. The test data remains unseen so that we can test how well our model performs after it's trained. This is an essential part of supervised learning. We also need to extract features from the text to predict the label. We will use a bag of words vectorizer built into Scikit-Learn to do so. After the model is trained, we can then test it using the test dataset. There are also other methods to evaluate model performance, such as k-fold cross-validation, and you could check out DataCamp's machine learning curriculum to learn that and more. In this video, we'll build our first Scikit-Learn vectors from the movie plot and genre dataset. We have a dataset full of movie plots and what genre the movie is, either action or sci-fi. We want to create bag of words vectors for these movie plots to see if we can predict the genre based on the words used in the plot summary. To do so, we first need to import some necessary tools from Scikit-Learn. Once the data is loaded, we can create Y, which traditionally refers to the labels or outcome you want the model to learn. We can use the sci-fi column, which has 1 if the movie is sci-fi and 0 if it is action. Then, Scikit-Learn's train test split function can be used to split the data frame into training and testing data. This method will split the features, which is the plot summary or column plot, and the labels Y based on a given test size, such as 0.33, representing 33%. I've also set random state so that we can have a repeatable result. It operates similar to setting a random seed and ensures I get the same results when I run the code again. The function will take 33% of rows to be marked as test data and remove them from the training data. The test data is later used to see what my model has learned. The resulting data from train test split are training data as xtrain, and training labels as ytrain, and testing data as xtest, and testing labels as ytest. Next, we create a count vectorizer, which turns my text into bag of words vectors similar to a Gensim corpus. It will also remove English stopwords from the movie plot summaries as a pre-processing step. Each token now acts as a feature for the machine learning classification problem, just like the flower measurements in the iris dataset. We can then call fit-transform on the training data to create a bag of words vectors. Fit-transform is a handy shortcut which will call the model's fit and then transform methods, which here generates a mapping of words with IDs and vectors representing how many times each word appears in the plot. Fit transform operates differently for each model, but generally fit will find parameters or norms in the data, and transform will apply the model's underlying algorithm or approximation, similar to preprocessing, but with a specific use case in mind. For the count vectorizer class, fit transform will create the bag of words dictionary and vectors for each document using the training data. After calling fit transform on the training data, we call transform on the test data to create bag of words vectors using the same dictionary. The training and test vectors need to use a consistent set of words so the trained model can understand the test input. If we don't have much data, there can be an issue with words in the test set which don't appear in the training data. This will throw an error, so you need to either add more training data or remove the unknown words from the test data set. In only a few lines of Python, we've transformed text into bag of words vectors and generated test and training datasets. Scikit-Learn is a great aid in helping make NLP machine learning simple and accessible. In this video, we'll use the features we've extracted to train and test a supervised classification model. A naive Bayes model is commonly used for testing NLP classification problems because of its basis in probability. Naive Bayes' algorithm uses probability, attempting to answer the question, if given a particular piece of data, how likely is a particular outcome? For example, thinking back to our movie genres dataset, if the plot has a spaceship, how likely is it that the movie is sci-fi? And given a spaceship and an alien, how likely now is it a sci-fi movie? Each word acts as a feature for our count vectorizer, helping classify our text using probability. Naive Bayes has also been used for text classification problems since the 1960s and continues to be used today despite the growth of many other models, algorithms, and neural network architectures. That said, it's not always the best tool for the job, but it is a simple and effective one, and you'll use it to build a fake news classifier. We'll use Scikit-Learn's naive Bayes to take a look at our sci-fi versus action plot classification problem. Recall the data we're using is simply IMDb plot summaries and whether the movie is science fiction or action. First, we import the naive Bayes model class, multinomial naive Bayes, which works well with count vectorizers as it expects integer inputs. Multinomial naive Bayes is also used for multiple label classification. This model may not work as well with floats, such as Tf-Idf weighted inputs. Instead, use support vector machines or even linear models, although I recommend trying naive Bayes first to determine if it can also work well. We use the metrics module to evaluate model performance. We initialize our class and call fit with the training data. If you recall from the previous video, this will determine the internal parameters based on the dataset. We pass the training count vectorizer first and the training labels second. After fitting the model, we call predict with the count vectorizer test data. Predict will use the trained model to predict the label based on the test data vectors. We save the predicted labels in variable pred to test the accuracy. Finally, we test accuracy using accuracy score from the metrics module and passing the predicted and test labels. Accuracy for our model means the percentage of correct genre guesses out of total guesses. Our model has about 86% accuracy, which is pretty good for a first try. You'll be applying the multinomial naive Bayes classifier to the fake news dataset in the following exercises. To further evaluate our model, we can also check the confusion matrix, which shows correct and incorrect labels. The confusion matrix function from the metrics module takes the test labels, the predictions, and a list of labels. If the label list is not passed, Scikit-Learn will use Python ordering. The confusion matrix is a bit easier to read when we transform it into a table. The first value and the last value of the matrix, or the main diagonal of the matrix, show true scores, meaning true classification of both action and sci-fi films based on the plot bag of words vectors. In a confusion matrix, the predicted labels are shown across the top and the true labels are shown down the side. This confusion matrix shows 864 sci-fi movies incorrectly labeled as action and 563 action movies incorrectly labeled as sci-fi. We can see from the distribution of true positives and negatives that our dataset is a bit skewed. We have many more action films than sci-fi. This could be one reason that our action movies are predicted more accurately. You've learned so much about natural language processing fundamentals in this course. Congratulations! In this video, we'll talk about how complex these problems can be and how to use the skills you've learned to start a longer exploration of working with language in Python. In the exercises, you will apply some extra investigation into your fake news classification model to see if it has really learned what you wanted. Translation, although it might work well for some languages, still has a long way to go. This tweet by Lupin, attempting to translate some legal or bureaucratic text about economics and industry, is a pretty funny and also sadly accurate example of when using word vectors between two languages can end poorly. The German text uses words like Nationalökonomie and Wirtschaftswissenschaft, but the English text simply says the economics of economics, including economics, and so forth, is part of economics. The German text has many different words related to economics, and they are all simply closest to the English vector for economics, leading to a hilarious but woefully inaccurate translation. Sentiment analysis is far from a solved problem. Complex issues like snark or sarcasm and difficult problems with negation, for example, I liked it, but it could have been better, make it an open field of research. There is also active research regarding how separate communities use the same words differently. This is a graphic from a project called Social Scent, created by a group of researchers at Stanford. The project compares sentiment changes in words over time and from different communities. Here, the authors compare sentiment in word usage between two different Reddit communities, 2X, which is woman-centered, and sports. The graphic illustrates the same word can be used with very different sentiments depending on the communal understanding of that word. Finally, we must remember language can contain its own prejudices and unfair treatment towards groups. When we then train word vectors on these prejudiced texts, our word vectors will likely reflect those problems. Here, we take a gendered language, like English, and translate it to Turkish, a language with no gendered pronouns. When we click to translate it back, we see that the genders have switched. This phenomenon was studied in a recent article by a Princeton researcher, Eileen Kaliskin, alongside several ethical machine learning researchers. She also gave a talk at the 33rd Annual Chaos Computer Club conference in Hamburg, which I can definitely recommend viewing. As we have seen in just a few examples, the field of natural language processing still has plenty of unsolved problems. In fact, our fake news detector is likely one of them. Let's do some investigation into what it's learned to determine if the model will be widely applicable or if the problem is likely more complex than simple word counts.
Welcome to the course. In this course, we will build upon some of your Python skills and introduce methods for sentiment analysis using movie and product reviews, Twitter data, and a lot of literary examples. Let's start with defining what sentiment analysis is. Sentiment analysis, also called opinion mining, is the process of understanding the opinion of an author about a subject. In other words, what is the emotion or opinion of the author of the text about the subject discussed? In a sentiment analysis system, depending on the context, we usually have three elements. First is the opinion or an emotion. An opinion, also called polarity, can be positive, neutral, or negative. An emotion could be qualitative, like joy, surprise, or anger, or quantitative, like rating a movie on the scale from 1 to 10. The second element in a sentiment analysis system is the subject that is being talked about, such as a book, a movie, or a product. Sometimes one opinion could discuss multiple aspects of the same subject. For example, the camera on this phone is great, but its battery life is rather disappointing. The third element is the opinion holder or entity expressing the opinion. Sentiment analysis has many practical applications. In social media monitoring, we don't just want to know if people are talking about a brand, we want to know how they're talking about it. Social media isn't our only source of information. We can also find sentiment on forums, blogs, and the news. Most brands analyze all of these sources to enrich their understanding of how customers interact with their brand, what they're happy or unhappy about, and what matters most to consumers. Sentiment analysis is thus very important in brand monitoring and in fields such as customer and product analytics and market research and analysis. Let's look at the first dataset we will use in this course, a sample of IMDb movie reviews. We have two columns, one for the text of the review and a second one called label, which expresses the overall sentiment. The category or class 1 means positive and 0 means negative. Let's find out how many positive and negative reviews we have in the data. To do this, we call the value counts method on the label column. The output is the number of negative reviews, the 0 class, and positive reviews, the class 1. If we want to see the number of positives and negatives as a percentage, we can divide the expression by the number of rows, which we obtain with the len method. We see that the samples are balanced. Around half of the reviews are positive and half are negative. How long is the longest review? To find that, we create a pandas series called length reviews by selecting the review column of the dataset, followed by .str.len. str is short for string. We need to call the string function to transform the series of reviews to a string. If we skip it, we get an attribute error when the len function is called. The result returns a pandas series with the number of characters in each review. To find the length of the longest review, we need to call the max function on the length review series. To find the shortest review, we call the min function on the length review series instead of the max function. Welcome back! In the previous video, we learned what sentiment analysis is and why it is useful. But how do we even start with a sentiment analysis task? Sentiment analysis tasks can be carried out at different levels of granularity. First is document level. This is when we look at the whole review of a product, for example. Second is the sentence level. This refers to determining whether the opinion expressed in each sentence is positive, negative, or neutral. The last level of granularity is the aspect level. The aspect refers to expressing opinions about different features of a product. Imagine a sentence such as, "The camera in this phone is pretty good, but the battery life is disappointing." It expresses both positive and negative opinions about the phone, and we might want to be able to say which features of the product clients like and which they don't. The algorithms used for sentiment analysis could be split into two main categories. The first is rule or lexicon-based. Such methods most commonly have a predefined list of words with a valence score. For example, nice could be +2, good +1, terrible -3, and so on. The algorithm then matches the words from the lexicon to the words in the text and either sums or averages the scores in some way. As an example, let's take the sentence, "Today was a good day." Each word gets a score, and to get the total valence, we sum the words. In this case, we have a positive sentence. A second category is automated systems, which are based on machine learning. This is going to be our focus in this course. The task is usually modeled as a classification problem where, using some historical data with known sentiment, we need to predict the sentiment of a new piece of text. We can calculate the value score of a text using Python's TextBlob library. We continue working with our "today was a good day" string. We import the TextBlob function from the TextBlob package and apply it to our string. A TextBlob object is like a Python string which has obtained some natural language processing skills. We can call different properties of the TextBlob object. We're interested in its sentiment, that's why we call sentiment on our TextBlob. The sentiment property returns a tuple. Polarity, which is measured on the scale from -1 to 1, where -1 is very negative, 0 is neutral, and +1 is very positive. Our example, "today was a good day," carries positive emotion, and thus will have a positive polarity score of 0.7. The second element in the tuple displays the subjectivity, measured from 0 to 1, where 0 is very objective and 1 is very subjective. So our example is rather positive and subjective. Which method should one use? A machine learning sentiment analysis relies on having labeled historical data, whereas lexicon-based methods rely on having manually created rules or dictionaries. Lexicon-based methods fail at certain tasks because the polarity of words might change with the problem, which will not be reflected in a predefined dictionary. However, lexicon-based approaches can be quite fast, whereas machine learning models might take a while to train. At the same time, machine learning models can be quite powerful. So the jury is still out on that one. Many people find that a hybrid approach tends to work best in many usually complex scenarios. Welcome back! Chances are high that you have seen a word cloud before. A word cloud is an image composed of words with different sizes and colors. They can be especially useful in sentiment analysis. Have you ever wondered how such an image is generated? In this video, we will learn how to create a word cloud in Python. Word clouds, also called tag clouds, are used across different contexts. In the most common type of word clouds, and the one we will be using in this course, the size of the text corresponds to the frequency of the word. The more frequent the word is, the bigger and bolder it will appear on the word cloud. Remember how we found the longest movie review? This word cloud is generated using only the words in one of the longest reviews. Which movie do you guess the review is talking about? I think we can agree it is about the Titanic. Why are word clouds so popular? First of all, they can reveal the essential. We saw in our word cloud the word Titanic really popped out. Second, unless told otherwise, they will plot all the words in a text, and a quick scan of the image can provide an overall sense of the text. Last but not least, they are easy to understand and quite fun. However, they have their drawbacks. Sometimes they tend to work less well. All the words plotted on the cloud might seem unrelated, and it could be difficult to draw a conclusion based on a crowded word cloud. Secondly, if the text we work with is large, a word cloud might require quite a lot of preprocessing steps before it appears sensible and uncluttered. Now let's create a word cloud in Python. To do that, we can use the word cloud function from the word cloud package. We will have to import matplotlib.pyplot as well, which will allow the word cloud to plot on its base. Let's define a string called Two Cities, which captures the first sentence of Dickens' Tale of Two Cities. Note how the text carries many emotionally charged words. After we have imported the package, we build the cloud by calling the word cloud function, followed by the generate method, which takes as argument the text, in our case, the Two Cities string. The word cloud function has many arguments. We will not cover all of them here, but if you want to learn what they are, just type word cloud in the shell. You can change things such as the background color, the size and font of the words, their scaling, and others. One interesting argument you can specify is the stopwords, which will remove words such as the, and, to, from, and so on. We will cover what stopwords are in detail in a later video. The result, cloud2cities, is a word cloud object. If we want to display the generated word cloud object, we need to use some Matplotlib functionality. We call plot_imshow, specifying our cloud2cities as an argument. We also specify the interpolation to be bilinear. All this does is make the image appear more smoothly. The imshow function thus creates the figure. We specify we don't want the image to display x and y axis, and finally call the show method. The imshow function has created the figure, but we need to call show to display it. We see the word cloud we generated on this piece of text. Which words pop out the most? Welcome to the next chapter of this course. We proceed in our journey by embarking on the first step in performing the sentiment analysis task, transforming our text data to numeric form. Why do we need to do that? A machine learning model cannot work with the text data directly, but rather with numeric features we create from the data. We start with a basic and crude but often quite useful method called bag of words. A bag of words approach describes the occurrence or frequency of words within a document or a collection of documents, called corpus. It basically comes down to building a vocabulary of all the words occurring in the document and keeping track of their frequencies. Before we continue with the discussion of bag of words, we will introduce the data we will use throughout the chapter, namely reviews of Amazon products. The dataset consists of two columns. The first contains the score, which is 1 if positive and 0 if negative. The second column contains the actual review of the product. Let's see how bag of words would work applied to an example review. Imagine you have the following string. This is the best book ever. I love the book and highly recommend it. The goal of a bag of words approach would be to build the following dictionary-like output. This occurs once in our string, so it has a count of 1. Is occurs once, the occurs 2 times, and so on. One thing to note is that we lose the word order and grammar rules. That's why this approach is called a bag of words, resembling dropping a bunch of items in a bag and losing any sense of their order. This sounds straightforward, but sometimes deciding how to build the vocabulary can be complex. We discuss some of the trade-offs we need to consider in later chapters. When we transform the text column with a bag of words, the end result looks something like the table that we see, where the column is the word, also called token, and the row represents how many times we have encountered it in the respective review. How do we execute a bag of words process in Python? The simplest way to do this is by using the count vectorizer from the text library in the Scikit-Learn feature extraction submodule. In Python, we import the count vectorizer from scikit-learn.featureextraction.text. In the count vectorizer function, for the moment we leave the default functional options except for the max features argument, which only considers the features with highest turn frequency. In other words, it will pick the 1,000 most frequent words across the corpus of reviews. We need to do that sometimes for memory's sake. We use the fit method from the count vectorizer calling fit on our text column. To create a bag of words representation, we call the transform method applied again to our text column. The result is a sparse matrix. A sparse matrix only stores entities that are non-zero, where the rows correspond to the number of rows in the dataset and the columns to the bag of words vocabulary. To look at the actual contents of a sparse matrix, we need to perform an additional step to transform the bag to a dense NumPy array using the toArray method. We can build a pandas data frame from the array, where the columns' names are obtained from the getFeatureNames method of the vectorizer. This returns a list where every entry corresponds to one feature. You might remember from an earlier video that with the bag of words approach, the word order is discarded. Imagine you have a sentence such as I am happy, not sad, and another one, I am sad, not happy. They will have the same representation with a bag of words, even though the meanings are inverted. In this case, putting not in front of the word, which is also called negation, changes the whole meaning and demonstrates why context is important. There is a way to capture the context when using a bag of words by, for example, considering pairs or triples of tokens that appear next to each other. Let's define some terms. Single tokens are what we have used so far and are also called unigrams. Bigrams are pairs of tokens. Trigrams are triples of tokens. And a sequence of n tokens is called n-grams. Let's illustrate that with an example. Take the sentence, the weather today is wonderful, and split it using unigrams, bigrams, and trigrams. With unigrams, we have single tokens. With bigrams, pairs of neighboring tokens. With trigrams, triples of neighboring tokens. It is easy to implement n-grams with the count vectorizer method. To specify the n-grams, we use the n-gram range parameter. The n-gram range is a tuple where the first parameter is the minimum length and the second parameter is the maximum length of tokens. For instance, n-gram range equals to 1, 1 means we will use only unigrams. 1, 2 means we will use unigrams and bigrams, and so on. It's not easy to determine what is the optimal sequence you should use for your problem. If we use longer token sequence, this will result in more features. In principle, the number of bigrams could be the number of unigrams squared, trigrams the number of unigrams to the power of 3, and so forth. In general, having longer sequences results in more precise machine learning models, but this also increases the risk of overfitting. An approach to find the optimal sequence length would be to try different lengths in something like a grid search and see which results in the best model. Determining the length of token sequence is not the only way to determine the size of the vocabulary. There are a few parameters in the count vectorizers that can also do that. You might remember we set the max features parameter. The max features can tell the count vectorizer to take the top most frequent tokens in the corpus. If it is set to none, all the words in the corpus will be included. So this parameter can remove rare words, which depending on the context may or may not be a good idea. Another parameter you can specify is maxDF. If given, it tells count vectorizer to ignore terms with a higher than the given frequency. We can specify it as an integer, which will be an absolute count, or float, which will be a proportion. The default value of maxDF is 1, which means it does not ignore any terms. Very similar to maxDF is minDF. It is used to remove terms that appear too infrequently. It again can be specified either as an integer, in which case it will be a count, or a float, in which case it will be a proportion. The default value is 1, which means ignore terms that appear in less than one document. Thus, the default setting does not ignore any terms. When we have a sentiment analysis task, which we will solve with machine learning, having extra features usually results in a better model. Our goal in this video is to enrich the dataset of choice with extra features related to the text capturing the sentiment. We continue to work with the Amazon product reviews dataset. Remember that the first column contains the numeric score and the second column the review itself. In my own experience, some very predictive features say something about the complexity of the text column. For example, one could measure how long each review is, how many sentences it contains, or say something about the parts of speech involved, punctuation marks, etc. Remember, we employed the bag of words approach to transform each review to numeric features, counting how many times a word occurred in the respective review. Here, we stop one step earlier and only split the reviews in individual words, usually called tokens, though a token can be a whole sentence as well. We will work with the NLTK package and concretely the word tokenize function. Let's apply the word tokenize function to our familiar ANA-K string. The returned result is a list, where each item is a token from the string. Note that not only words but also punctuation marks are originally assigned as tokens. The same would have been the case for digits if we had any in our string. Now we have to apply the same logic but to our column of reviews. One fast way to iterate over strings is by using list comprehension. A quick reminder on list comprehensions. They are like flattened out for loops. The syntax is an operation we perform on each item in an iterable object, such as a list. In our case, a list comprehension will allow us to iterate over the review column, tokenizing every review. The result is going to be a list. If we explore the type of the first item, for example, we see it is also of type list. This means that our word tokens is a list of lists. Each item stores the tokens from a single review. Now that we have our word tokens list, we only need to count how many tokens there are in each item of word tokens. We start by creating an empty list, to which we will append the length of each review as we iterate over the word tokens list. In the first line of the for loop, we find the number of items in the word tokens list using the len function. Since we want to iterate over this number, we need to surround the len by the range function. In the second line, we find the len of each iterable and append that number to our empty list len tokens. Lastly, we create a new feature for the length of each review. Note that we did not address punctuation, but you can exclude it if it suits your context better. You can even create a new feature that measures the number of punctuation signs. In our context, a review with more punctuation signs could signal a very emotionally charged opinion. It's also good to know that we can follow the same logic and create a feature that counts the number of sentences, where one token will be equal to a sentence and not to a single word. If we check how the product reviews dataset looks like, we see the n tokens column we created. It shows the number of words in each review. Often in real applications, not all documents carrying sentiment will be in English. We might want to detect what language is used or build specific features related to language. In Python, there are a few libraries that can detect the language of a string. In this course, we will use LangDetect because it is one of the better performing packages. But you can follow the same structure using another package. We first import the detect length function from the LangDetect package. Now imagine we have a string called foreign, which is a sentence in another language. Our goal is to identify its language. We apply the detect length function to our string. This function will return a list. Each item of the list contains a pair of a language and a number saying how likely it is that the string is in this particular language. In this case, we observe only one item in the list, namely Spanish. That's because the function is fairly certain the language is Spanish. In other cases, we might get longer lists, where the most likely candidate languages will appear first, followed by less likely ones. In real applications, we usually work not with a single string, but with many strings, often contained in a column of a dataset. A common problem is to detect the language of each of the strings and capture the most likely language in a new column. How to do that? We again start by importing the detect length function from the LangDetect package. We import our familiar dataset with product reviews. The steps we follow next are quite similar to our approach when capturing the length of a review. First, we create an empty list called languages. We want to iterate over the rows of our dataset using a for loop. In the first line of the loop, we apply the len function to our dataset, which returns the number of rows. We still need to call the range function since we want to iterate over the number of rows. In the second line of the loop, we apply the detect length function on the review column of the dataset, which is the second column in our case, while selecting one row at a time. We want to store each detected language in an item in a list, therefore we append the result of detect lengths to the empty list languages. When we print languages, we see that it is a list of lists, where each element contains the detected language of the respective row and how likely that language is. In some cases, the individual lists contain more than one item. We have one more step before we create our language feature. We saw that languages is a list of lists. We want to extract the first element of each list within languages, since the first item is always the most likely language. One fast way to do that is by list comprehension. Let's break down the command in steps. For example, let's take the first element of the languages and split it on a colon sign. After that, we extract the first element of the resulting split, returning left bracket ES. Finally, since there is a left bracket before the language, we select everything from the second element onwards, resulting in ES for Spanish. To write the list comprehension, we put these steps together by iterating over each item in our list of lists. Lastly, we assign the cleaned list to a new feature called language. In every language, there are words that occur too frequently and are not very informative. Sometimes it is useful to get rid of them before we build a machine learning model. Words that occur too frequently and are not very informative are called stopwords. But how do we know which words are not informative? In every language, there is a set of words that most practitioners agree are not useful and should be removed when performing a natural language processing task. For instance, in English, the definite and indefinite article, the on, conjunctions such as and, but, for, and prepositions such as on, in, at, etc. are stopwords. Secondly, depending on the context, we might want to expand the standard set of stopwords. For example, in the movie reviews dataset, we might want to exclude words such as film, movie, cinema, etc. Maybe you recall from a previous lesson that we built word clouds using movie reviews. Here is an example of two word clouds using the movie reviews. In the picture on the left, the stopwords have not been removed. Words that pop up are film and BR, which is an indication for a line break. In the cloud on the right side, stopwords have been removed, and now we see words such as character, see, good, story. How do we remove stopwords when creating a word cloud? Let's start by reviewing how we build a word cloud. First, we import the word cloud function from word cloud. We also import the default list of stopwords from word cloud. To create our list of stopwords, we can take a set of the default list. A set is like a list, but with unique, not repeating items. We can update a set of stopwords by calling update and providing a list to it. We pass our list of stopwords called myStopwords to the stopwords argument in the word cloud function. Then we display it. So, the only new argument we added here is defining the list of stopwords. Everything else stays the same. Removing non-informative words when we are building a bag of words transformation can also be very useful. This can easily be incorporated in the count vectorizer function. First, we need to import the list of default English stopwords from the same featureextraction.txt package from Scikit-Learn. Let's assume we want to enrich this default list with movie-specific words. To do that, we call the union function on the default list. Remember that the union of two sets A and B consists of all elements of A and all elements of B, such that no elements are repeated. In our case, The union will add the new words to the list of default stopwords if that word is not already there. To use the constructed set, we specify the stopwords argument in the count vectorizer to be equal to our defined set. Everything else stays the same and should look pretty familiar by now. One important thing to note is that using stopwords will reduce the size of the vocabulary we build using a pack of words or another approach. You may have noticed while working with the airline sentiment data from Twitter that the text contains many digits and other characters. Sometimes we may want to exclude them from our numeric representation. If we work with a string, how can we make sure we extract only certain characters? There are a few useful functionalities we will review here. We can use string comparison operators, such as isAlpha, which returns true if a string is composed only of letters and false otherwise. isDigits returns true if a string is composed only of digits. And finally, isAllNum returns true if a string is composed only of alphanumeric characters, in other words, letters and digits. String operators can improve some of the features we created earlier. As a reminder, in a previous video, we used a list comprehension to iterate over each review of the product reviews dataset and create word tokens from each review. We can adjust our original code. If we want to retain only tokens consisting of letters, for example, we can use the isAlpha operator in a second list comprehension. Since the result of the first list comprehension is a list of lists, we first need to iterate over the items in each inner list, filtering out those tokens that are not letters. This is what happens in the first part of the list comprehension, enclosed in the inner brackets. In the second part, we're iterating over the lists, basically saying that we want to perform this filtering across all lists in the word tokens list. When we compare the length of the first item of word tokens and the cleaned tokens lists, we see that the filtering decreased the number of tokens, as we might expect. Regular expressions are a standard way to extract certain characters from a string. Python has a built-in package called RE, which allows you to work with regular expressions. We will not cover regular expressions in depth here, but a quick reminder on the syntax. We import the RE package. Then imagine we have a string #wonderfulday and we want to extract a hash followed by any letter, capital or small. One standard way to do is by calling the search function on our string, specifying the regular expression. In our case, it starts with a hash and is followed by either an upper or lowercase letter. When we print the result, we see that it is a match object, showing how large the match is. In our case, the span is 2, and also the exact characters that were matched. Our familiar count vectorizer takes regular expression as an argument. The default pattern used matches words that consist of at least 2 letters or numbers, \w, and which are separated by word boundaries, \b. It will ignore single-lettered words and will split words such as don't and haven't. If we are fine with this default pattern, we don't need to change any arguments in the count vectorizer. If we want to change it, we can specify the token pattern argument. If we want the vectorizer to ignore digits and other characters and only consider words of 2 or more letters, we can use the specify token pattern. In fact, there are multiple ways to specify this. It doesn't mean the one specified here is the only correct or best way to accomplish this. Feel free to experiment with this. Note, however, that we need to add an R before the regular expression itself. In a language, words are often derived from other words, meaning words can share the same root. When we create a numeric transformation of a text feature, we might want to strip a word down to its root. This is the topic of this lesson. This process is called stemming. More formally, stemming can be defined as a transformation of words to their root forms, even if the stem itself is not a valid word in the language. For example, staying, stays, state will be mapped to the root stay, and house, houses, housing will be mapped to the root HOUS, house. In general, stemming will tend to chop off suffixes such as ed, ing, er, as well as plural or possessive forms. Lemmatization is quite a similar process to stemming, with the main difference that with lemmatization, the resulting roots are valid words in the language. Going back to our examples of words derived from stay, lemmatization reduces them to stay, and words derived from house are reduced to the noun house. You might wonder when to use stemming and when lemmatization. The main difference is in the obtained roots. With lemmatization, they are actual words, and with stemming they might not be. So, if in your problem it's important to retain words, not only roots, lemmatization would be more suitable. However, if you use NLTK, which is what we will use in this course, stemming follows an algorithm which makes it faster than the lemmatization process in NLTK. Furthermore, lemmatization is dependent on knowing the part of speech of the word you want to lemmatize. For example, whether we want to transform a noun, a verb, an adjective, etc. One popular stemming library is the Porter stemmer in the NLTK.stem package. The Porter stemmer is not the only stemmer in NLTK, but it's quite fast and easy to use, so it's often a standard choice. We call the Porter stemmer function and store it under the name Porter. We can then call porter.stem on a string, for example, wonderful. The result is wonder. Stemming is possible using other languages as well, such as Danish, Dutch, French, Spanish, German, etc. To use foreign language stemmers, we need to use the Snowball stemmer package. We can specify in the stemmer the foreign language we want to use. Then we apply the stem function on our string. For example, we have imported a Dutch stemmer and fed it a Dutch verb. The result is the root of the verb. If you apply the Porter stemmer on a sentence, the result is the original sentence. We see nothing has changed about our "today is a wonderful day" sentence. We need to stem each word in the sentence separately. Therefore, as a first step, we need to transform the sentence into tokens using the familiar word tokenize function. In the second step, we apply the stemming function on each word of the sentence using a list comprehension. The lemmatization of string is similar to stemming. We import the WordNet lemmatizer from the NLTK stem library. It uses the WordNet database to look up lemmas of words. We call the WordNet lemmatizer function and store it under the name WN-Lemmatizer. We can then call WN-Lemmatizer.lemmatize on wonderful. Note that we have specified a part of speech, given that by the pos argument. The default pos is noun or n. Here we specify an adjective, that's why pos is equal to a. The result is wonderful. If you would recall, stemming returned wonder as a result. We have extensively worked with the back of words and applied it using Count Vectorizer in Python. As powerful as back of words can be, sometimes we might want to try slightly more sophisticated approaches. In this video, we will talk about one of them, an approach called Tf-Idf, term frequency inverse document frequency. The term frequency tells us how often a given word appears within a document in the corpus. Each word in a document has its own term frequency. The inverse document frequency is commonly defined as the log ratio between the total number of documents and the number of documents that contain a specific word. What inverse document frequency means is that rare words will have a high inverse document frequency. When we multiply the term frequency Tf and inverse document frequency Idf scores, we obtain the Tf-Idf score of a word in a corpus. With back of words, words could have different frequency counts across documents but we did not account for the length of a document, whereas Tf-Idf score of a word incorporates the length of a document. Tf-Idf will also highlight words that are more interesting. In other words, words that are common in a document but not across all documents. However, note that interesting does not have to relate to a positive or a negative review. It is purely an unsupervised approach. In our Twitter sentiment analysis, names of airline companies such as United and Virgin America are likely to have low Tf-Idf scores since they occur many times and across many documents or tweets. If a tweet talks a lot about the check-in service of a company and there are not many other tweets discussing the topic, words in this tweet are likely to have a high Tf-Idf score. Note that since Tf-Idf penalizes frequent words, there is less of a need to explicitly define stopwords. We can still remove stopwords, of course, to restrict the size of our vocabulary. Even though Tf-Idf is relatively simple, it is quite commonly used in information retrieval and search engines as a way to rank the relevance of the returned queries. In Python, you can apply Tf-Idf by importing the Tf-Idf vectorizer from Scikit-Learn.featureextraction.txt. The Tf-Idf vectorizer is similar to the count vectorizer, and so are the arguments it takes. We can define the maximum number of features by max features, the type of n-grams to use by specifying n-grams range, the stopwords argument, token pattern, maxdf, and mindf. We fit the Tf-Idf vectorizer to the text column of the tweets dataset. Then we transform it the same way we did with the count vectorizer. The Tf-Idf vectorizer also returns a sparse matrix. If you recall, a sparse matrix is a matrix with mostly zero values, storing only the non-zero values. We need to transform the sparse matrix to an array and specify the feature names, using the same syntax as with the count vectorizer. Inspecting the top 5 rows of the newly created dataset, we see that the output is quite similar to a bag of words. Each column is a feature, and each row contains the Tf-Idf score of the feature in a given tweet. The values are floating numbers, and many of them are 0. In this final chapter, we will use a supervised learning model to predict the sentiment. Imagine we are working with the product reviews. A supervised learning task will try to classify any new review as either positive or negative based on already labeled reviews. This is what we call a classification problem. In the case of the product and movie reviews, we have two classes, positive and negative. This is a binary classification problem. The airline sentiment Twitter data has 3 categories of sentiment: positive, neutral, and negative. This is a multi-class classification problem. One algorithm commonly applied in a classification task is a logistic regression. You might be familiar with the linear regression, where we fit a straight line to approximate a relationship, shown in the graph on the left. With a logistic regression, instead of fitting a line, we are fitting an S-shaped curve called a sigmoid function. A property of this function is that for any value of x, y will be between 0 and 1. When performing linear regression, we are predicting a numeric outcome, say the sale price of a house. With logistic regression, we estimate the probability that the outcome, sentiment, belongs to a particular category, positive or negative, given the review. Since we're estimating a probability and want an output between 0 and 1, we model the x values using the sigmoid, or also called logistic function, as shown on the graph. For more details on logistic regression, refer to other courses on DataCamp. In Python, we import the logistic regression from the Scikit-Learn.linear model library. Keep in mind that the Scikit-Learn API works only with continuous variables. It also requires either a data frame or an array as arguments and cannot handle missing data. Therefore, all transformation of the data needs to be completed beforehand. We call the logistic regression function and create a logistic classifier object. We fit it by specifying the X matrix, which is a NumPy array of our features or a pandas data frame, and the vector of targets Y. How do we know if the model is any good? We look at the discrepancy between the predicted label and what was the real label for each instance or observation in our dataset. One common metric to use is the accuracy score. Though not appropriate in all contexts, it is still useful. Accuracy gives us the fraction of predictions that our model got right. The higher and closer it is to 1, the better. One way we can calculate the accuracy score of a logistic regression model is by calling the score method on the logistic regression object. It takes as arguments the X matrix and Y vector. Alternatively, we can use the accuracy score function from Scikit-Learn.metrics. There is an accuracy score function apart from the score function because different models have different default score metrics. Thus, the accuracy score function always returns the accuracy, but the score function might return other metrics if we use it to evaluate other models. Here, we need to explicitly calculate the predictions of the model by calling predict on the matrix of features. The accuracy score takes as arguments the vector of true labels and the predicted labels. We see in the case of logistic regression, both score and accuracy score return value of 0.9. In the previous video, we used all of the available data to build a logistic regression model and assess its accuracy. However, we want to make sure our machine learning model generalizes and performs well on unseen data. How to do that? To get any idea on how well a model will perform on unseen data, we randomly split the dataset in two parts, one used for training, building the model, and one for testing, evaluate the performance of the model. In some cases, when we want to tune the parameters of an algorithm, we might have three sets, training, testing, and validation, but this is out of scope for our course. The training set is usually around 70 or 80% of the whole dataset, and the rest is used for testing. In Python, we can perform a random train-test split using the train-test-split function from the Scikit-Learn model selection package. It takes as arguments arrays, lists, or data frames. The X train and test matrices and Y train and test vectors are the output of the train-test split. The first arguments we provide in the function are the features matrix X and labels vector Y. We can specify the proportion of the data going to testing. Here, it is equal to 0.2. Another parameter is the random state, which is the seed generator used to make the random split. It ensures that every time you perform the train test split on the same data, you will get the same instances in each set. We can also specify the stratify argument. If we want to ensure that the train and test have similar proportion of both classes, we can do that by specifying stratify to be equal to Y. Let's revisit our logistic regression example executed after train test split. We create the logistic regression object and fit it on the training set. We can calculate the accuracy on the training data, calling score on the logistic regression with arguments xtrain and ytrain. We can also calculate the accuracy score of the model using the test set xtest and ytest. It is slightly lower than the accuracy on the training data, which is usually the case. You may recall that another way to calculate the accuracy was to use the accuracy score function from Scikit-Learn.metrics. After we have built the logistic regression model, we apply predict to the logistic regression, specifying xtest as an argument. In the last step, we call the accuracy score on the true and predicted labels. The value is identical to the accuracy produced by the score function. The accuracy is a useful measure of a model's performance, but it's not always the most informative. We can instead use something called a confusion matrix. It shows the number of predicted and true values of each of the classes as displayed in the table. A confusion matrix will allow us to calculate the values in each cell and say how many observations of each class we have predicted correctly. For more details of when we would want to optimize for the different cells, refer to other DataCamp courses. In Python, we import the confusion matrix from the Scikit-Learn.metrics module. After we have built our logistic regression and predicted the test set labels, we call the confusion matrix, where we give as arguments the true and predicted labels. We have divided by the matrix by the length of the y vector in order to obtain proportions in the cells of the matrix. Before we build the logistic regression using text features, we transform the text fields to numeric columns. As a result, we might end up having hundreds or even thousands of features, which can make the model quite complex. A complex model can occur in a few scenarios. If we use a very complicated function to explain the relationship of interest, we will inevitably fit the noise in the data. Such a model will not perform well when used to score unseen data. This is also called overfitting. A complex model could stem from including too many unnecessary features and parameters, especially with transformed text data where we might create thousands of extra numeric columns. These two sources of complexity often go hand in hand. One way to artificially discourage complex models is by the use of regularization. When using regularization, we are penalizing or restricting the function of the model. Regularization is applied by default in the logistic regression function from Scikit-Learn. It uses the so-called L2 penalty. The details of it are outside the scope of this course, but intuitively it's good to know that the L2 penalty shrinks all the coefficients towards zero, effectively reducing the impact of each feature. The parameter that determines the strength of regularization is given by C, which takes the default value of 1. Higher values of C correspond to less regularization. In other words, the model will try to fit the data as best as possible. Small values of C correspond to high penalization or regularization, meaning that the coefficients of the logistic regression will be closer to zero. The model will be less flexible because it will not fit the training data so well. How to find the most appropriate value of C? Usually, we need to test different values and see which one gives us the best performance on the test data. You should recall that when we trained the logistic regression model, we applied the predict function to the test set to predict the labels. The predict function returns a class, 0 or 1 if we are working with a binary classifier. However, instead of a class, we can predict a probability using the predict proba function. We again pass as an argument the test dataset. This returns an array of probabilities, ordered by the label of classes, first the class 0 and then the class 1. The probabilities for each observation are displayed on a separate row. The first value is the probability that the instance is of class 0 and the second of class 1. Therefore, it is common when predicting the probabilities to specify already that we want to extract the probabilities of the class 1. One important thing to know is that we cannot directly apply the accuracy score or confusion matrix to the predicted probabilities. If you do that in Scikit-Learn, you will get a value error. The reason is that the accuracy in the confusion matrix worked directly with classes. If we have predicted probabilities, we need to encode them as classes. The default is that any probability higher or equal to 0.5 is translated to class 1, otherwise to class 0. However, you can change that threshold depending on your problem. Imagine that only 1% of the reviews are positive, and you have built a model to predict whether a new review is positive or negative. In that context, you don't want to translate any predicted probability higher than 0.5 to class 1. This threshold should be much lower. Welcome back. In this video, we will put together all the steps we have applied in this course on sentiment analysis. I find myself applying these same steps in my work as a data scientist. We define sentiment analysis as the process of understanding the opinion of an author about a subject. Throughout the course, we work with examples of movie and Amazon product reviews, Twitter airline sentiment data, and different emotionally charged literary examples. We went through various steps to transform the text column, which contained the review, to numeric features. We finished our analysis by training a logistic regression model and predicting the sentiment of a new review based on the words in the text. Let's go through these steps in more detail. We started with exploring the review column in the movie's reviews dataset. We found which were the shortest and longest reviews. We also plotted word clouds from the movie reviews, which allowed us to quickly see which are the most frequently mentioned words in positive or negative reviews. Furthermore, we created features for the length of a review in terms of number of words and number of sentences, and we learned how to detect the language of a document. We continued with numeric transformations of the review features. We transformed the text using a bag-of-words approach and a Tf-Idf vectorizer. The bag-of-words created features corresponding to the frequency count of a word in a respective review or tweet, also called document in NLP problems. The term frequency inverse document frequency approach is similar to the bag-of-words, but it accounts for how frequently a word occurs in a document with respect to the rest of the documents. So we can capture important words, whereas words that occur frequently have lower Tf-Idf score. We used the count vectorizer and Tf-Idf vectorizer from Scikit-Learn.featureextraction.txt to construct each of the vectors. As a reminder of the syntax, we called the vectorizer function and fit and then transformed it to the text column in our data. There are many arguments we specified in the vectorizer. We dealt with stopwords, those frequently occurring and non-informative words. We had a video on n-grams, which allowed us to use different lengths of phrases instead of a single word. We learned how to limit the size of the vocabulary by setting any of a number of parameters, max features for the maximum number of features, max and min df, which tells the vectorizer to ignore terms with higher or lower than the specified frequency respectively. We could capture only certain characters using the token pattern argument. Last but not least, we learned about lemmas and stems and practiced lemmatizing and stemming of tokens and strings. We could adjust all these arguments, with the exceptions of lemmas and stems, in both the count and Tf-Idf vectorizers. In the final step, we used a logistic regression to train a classifier predicting the sentiment. We evaluated the performance of the model using metrics such as accuracy score and a confusion matrix. Since the goal is for our model to perform well on unseen data, we randomly split the data into a training and testing set. We use the training set to build the model and the test set to evaluate its performance. These are all very valuable skills and essential in performing a sentiment analysis task. Well done! This is our final video. You've learned the basics of performing a sentiment analysis using Python. We covered a lot of material in a short period of time, so you should be proud of yourself. We defined the three parts of a sentiment analysis system: sentiment, or an emotion of opinion holder, the subject being talked about, and the opinion holder. We classify the sentiment analysis algorithms as rule-based or automated. The rule or lexicon-based methods had a predefined list of words with a positivity score. The algorithm matches the words from the lexicon to the words in the text. Automated systems are based on machine learning. Using historical data with known sentiment, we predict the sentiment of a new piece of text. This is what we did in this course. In our sentiment analysis process, we followed 3 steps. After exploration of the data, we built new features related to the sentiment column. We then transformed it to numeric features. And finally, we built a machine learning model that classifies the sentiment.